Math 287, Cuesta College. I'm Joe Vasta, and we are covering 10.7, the second shifting theorem for the Laplace transforms. Now, 10.7 is the last one you'll be doing homework on. I might say something about 10.8 and 10.9 just to show you a few cool things about Laplace transforms. These are the rules of the Laplace transforms. These rules here are good rules to memorize, kind of like you memorized some derivatives when you first took Calculus 1. And, you know, if this were a face-to-face class, I would actually give you the first and second shifting theorem on the exam. So I'm going to actually just tell you what the second shifting theorem is. First, I'm going to state it incorrectly, because I want to show you something, that if we were living in a symmetric world, a perfect world, this shifting theorem, the second shifting theorem, look at the shift on the first shifting theorem. It's on the right-hand side. So on the second shifting theorem, the shift is on the left-hand side in the land of t. And so it's going to be g of t minus a. Okay, so I'm going to write this incorrectly. See, I left a little space there. In a perfect world, this is what would happen. The shift would be on the left. The e to the at would be on the right side. So it would be e, and it wouldn't be t, it would be as. And then you would have a g of s there. So maybe you can see that, you know, there's some symmetry going on with this one and this one. But we don't live in a perfect world. And so what we have to do is tell you what the real second shifting theorem is. This, first of all, is going to be a negative. Okay. And second of all, I left some space here so I can write u sub a of t, which is our unit step function. Now, the way I have it written now, that is legitimate. We are going to do a proof of the second shifting theorem. So let's go ahead and do a proof of the second shifting theorem. We are going to let f of t equal u sub a of t times g of t minus a, and we're going to go ahead and prove that second shifting theorem that I had written down on the piece of paper. So really the first thing that we want to do with the second shifting theorem is we want to, what we want to do with this function here is take the Laplace transform of it, and so that's what I'm going to do. So the Laplace transform of the function, remember I'm just using the definition, there's the e to the negative st, and then I have u sub a, and then the g of t minus a. Okay, the next thing I'm going to do is I'm going to make the realization that u sub a, the unit step function, is actually a bit. It's a 0 or a 1, and it happens to be 0 from time 0 to time a, and happens to be 1 from time a to infinity. So I'm going to break this integral up into the sum of two integrals. So there it is, 0 to a, we have 0, and that's just going to 0 out. And then a to infinity, we have a 1 there. Okay, so let's go ahead and write the next step. It's just that right there. And now I'm going to do a, well, we would say a u substitution, but I don't really want to use u because we already have a u sub a here. So I'm going to do a letter I do not have up there, which is weird that I don't have this letter in a math class. I'm going to do an x substitution. And x is going to equal t minus a. So I take the derivative of that, dx equals dt, and then also you can solve for t, so it says t equals x plus a. I'm going to put this stuff back into this integral. Now notice right here I have t equals a for the bottom limit of integration, and so if I replace the t with an x plus a equals a, I have an x plus a equals a, or x equals 0. So let's go ahead and write out the substitution. Now if I replace t goes to infinity with an x plus a constant goes to infinity, it looks like x is still going to go to infinity. I have the e to the negative s, there's the negative s, and then replace the t with an x plus a, g of, and then replace the t minus a with an x, and then dx equals dt. Okay, so that's what I have. So what I'm going to do is I'm going to use the property of exponents to kind of split this a little. And so I have this. I have integral from 0 to infinity, e to the negative s times x, e to the negative as, and then g of x dx. Now look at this. We are integrating now with respect to x and not with respect to t. Well, there's no t there. But there is a constant that I can pull out. I can pull out this guy right here, the factor that is above that red circle. I can pull that out of the integral sign. And so I have that right there. See, he came out. And now you might be able to recognize this. This right here is the Laplace transform. I know there's x's there instead of t's, but it's the Laplace transform of g. And so this is e to the negative as, Laplace transform of g, or e to the negative as, capital G of s. And so this gives us the second shifting theorem. Whoops, this mouse is moving. The second shifting theorem, which I had written down on the piece of paper. It's not completely symmetric to the first shifting theorem, but it does have the shift in the land of t, and it has the e to the power in the land of s. And the rest of this lecture on 10.7 will be working out some problems. So we just proved the second shifting theorem, which looks like this. So the rest of this lecture, we're just going to be doing problems that involve the second shifting theorem. And here's the deal. Remember when I did the first shifting theorem, I had the textbook way, and then I had the quick way. Well, there is the textbook way for the second shifting theorem, and then there's like the quicker way. But the problem is, and I've done this many semesters now, that there are some cases where you have to do both shifting theorems on one function. And so when you're doing this, the first shifting theorem the quick way, and the second shifting theorem the quick way, sometimes things get messed up. So I am actually going to do the second shifting theorem the textbook way, but I'm going to give you a little analogy here. So let's take a look at these two theorems, and I put them on a little card here, and I have the first shifting theorem because I'll just transfer this from sheet to sheet. And so look what we have. The second shifting theorem starts off with this. We have a function called f of t, which looks like this. Now your book's going to write these shifting theorems with f's there, and that's going to be very confusing because then they'll give you a function called f of t, which then would equal use of a of t, f of t minus a, and that's confusing. That's why I use the g's. So I have a function called f of t. I think about going from the land of t to the land of s by using stepping stones across this river. Okay, so what does this mean? My first stepping stone is to identify this, which is pretty easy to do. Going to the middle of the river, this could be a little slippery. This rock is a little wet sometimes, and so we have to figure out what g of t is. Now you might think that that's an easy thing, and it might be. And then you jump over to this rock, which is the Laplace transform, which is this guy right here, and then you jump to the shore and write out the whole answer. So that is the analogy I'm going to use, and then when we do the inverse transform, we'll start right here on this shore and then jump on these stones back to the shore where functions are written in terms of t. So let's go ahead and see if we can do this. I have Laplace transform, and actually I'm going to I was not thinking ahead on this, but now it makes perfect sense that I should be holding this like this. Okay. One more fold. Okay. So there it is. There's my drawing of the river that I'm trying to cross. And then also, wow, I've got all these cut and paste stuff, really cut stuff here. Okay, so I've got that there. Okay, so I'm trying to take the Laplace transform of functions that have a unit step function in it. So look what we have here. So we have this right here, and we see, so this could say find the Laplace transform. I have this guy right here, which I'm going to circle in blue. So my second shifting theorem, I'll always use blue, and the first shifting theorem, I'll always use the red. So that's how I'm going to do it. So let's go ahead and do this. Okay, so I'm here on the shore. I'm going to jump over here. I'm going to identify g of t minus a, and it's really g of t minus 5. So that's what I'm going to do. So g of t minus 5. Now this is not that hard to do, jumping to the first stone. It's actually going to be the part that is not circled. So this is just going to be t minus 5 cubed. Okay, so I'm here on this rock. Now I'm going to jump to this rock by finding g of t. A lot of you could tell me probably right now what g of t is. And if you're having a hard time doing that, you could replace all the t's in this equation with t plus 5, because look what happens. G of t plus 5 minus 5, so that's going to give you a g of t. And then this is t plus 5 minus 5, that's t cubed. So a lot of you probably guessed. We'll actually officially do that on the next one. So this is g of t equals t cubed. Okay, so now I've just stepped right there. So I'm in the middle of the river, and now I'm going to jump to this rock by taking the Laplace transform of g. And notice, I'm just following this as my roadmap. Hopefully it's all not blurry. Okay, so here's g of t. So to take the Laplace transform of t cubed, that's going to be 3 factorial over s to the 4th. So 3 factorial is 6 all over s to the 4th. Okay, now I'm on this stone and I'm ready to jump to the shore, and jumping from the shore to the first rock and from the last rock to the shore, it's pretty simple, because all I'm going to do is take this thing and multiply it by e to the negative as. And in our example, a is 5. So we're going to say negative 5s, e to the negative 5s. So my final answer, f of s, is going to be 6 over s to the 4th, and then we multiply it by e to the negative 5s. That gives me the Laplace transform using the second shifting theorem. This doesn't have to be blue when you're doing your homework. And when you do the second shifting theorem, there will always be a negative integer in front of the s up there. That's just the way it is, because a is always positive on the second shifting theorem. On the first shifting theorem, a could be positive or negative. So that's the deal. That's problem number 1. Let's go ahead and do problem number 2. In each of these problems, I'm going to keep the river. Well, hopefully in most of the problems, I'll keep the river right there, and this right there. And I should have actually put this all on one piece of paper. It's kind of on the bad side because I'm right-handed, so I might hit it a few times. Well, anyway, I've got f of t equals t minus 5 cubed times u7. It almost looks like the last problem. See the last problem? Look like that. So I changed this 5 to a 7 just to see what would happen, and it's actually going to make this problem a little bit more complicated. So the first thing I do is I go, oh, I'm doing a second shifting theorem because I see a u7 there. I circle it. Okay, and I identify the other part as g of t, see, g of t minus a, so g of t minus 7. G of t minus 7 is this other part, which is t minus 5 cubed. Okay, so now we've got that. We're on that stone and we're ready to jump to this slippery rock here. So how do we do that? I mean, it's not as easy as the last one where they both said t minus 5s. So I'm going to replace each of these t's. I'm trying to get a g of t there, so I'm going to replace each of those t's with a t plus 7. So when I do that, I have g of, so here I'll do this in purple, and maybe it's not that obvious in the video, t plus 7. That's what I replace that with. Then we have minus 7. This equals, this is t plus 7. It's like re-indexing when you're doing summation notation. And then I have minus 5. And then there's a cube there. So the left-hand side is going to be t plus 7 minus 7. That's t. So this is g. I'm using purple now. It's not to use that color regularly. So g of t equals, and then this is going to be t plus 2 cubed. T plus 2 cubed. Okay. So I'm right there in the middle of the river. I've got g of t, and I'm now supposed to take the Laplace transform. And so some of you might be saying, well, that looks like a shift, but when the shift is in the land of t, I should have a u sub a there, and I already took care of that. So I've got to figure out, well, how would I take the Laplace transform of this? I would have to multiply that out. How do you multiply t plus 2 cubed out? You go t plus 2 times t plus 2 times t plus 2. Or you use the shortcut, which is the binomial theorem. So the binomial theorem, you have Pascal's triangle. There's rho. Okay, so number is gotten by adding the two numbers above that number. Here's a 3 here, and this is a binomial. So this is rho 3. And I'm going to use those as the coefficients. 1, 3, 3, 1. This first term here within the parentheses is fully alive, meaning he's all powered up. T3, T2, T1, and now he's dead. T to the 0. This guy right here, 2 is completely dead at the beginning. 2 to the 0. Now, t to the 0 and 2 to the 0, those are just 1. So sometimes you don't even really have to write those there. And then this is 2 to the 1, 2 to the 2, 2 to the 3. So this right here gives you the 4 terms that this equals. So what is this? This is g of t equals, well, we'd start off with the t cubed. And then we have plus 3 times 2, so that's going to be 6t squared. And the next one's going to be, let's see, 2 squared, that's 4 times 3 is 12t. And then the last one is 2 cubed, which is 8. Okay, so we're still on the middle rock. We've been standing on that middle rock for a little bit because we're trying to get balanced so we can jump to this rock. And that's what we're going to do now. We're going to do the Laplace transform on this. So this is g of s equals, okay, 3 factorial over s to the 4th. So this is 6 over s to the 4th. And then we have Laplace transform of t squared is 2 factorial, which is 2, over s to the 3rd. So let me write this out so we don't confuse people. So this is 2 factorial over s to the 3rd. And then the next one is 12 times the Laplace transform of t to the 1 is 1 factorial. So that's 1 over s squared. And then the Laplace transform of a constant is just that constant over s. Okay. So now I'm standing on this rock, and I'm going to clean that up in there, but at the same time I'm going to jump to the shore. I'm going to jump to where f of s is and write down e to the negative as, and in this case it's going to be e to the negative 7s. So the Laplace transform of little f of t is big F of s. This equals e to the negative 7s, we're just following the formula here, times that right there. And so that's what I'm going to do. So this is going to be 6 over s to the 4th plus 12 over s cubed plus 12 over s squared plus 8 over s, and that gives us our answer. We successfully crossed the river, and we use the second shifting theorem. Let's move on and do some more examples. So we'll do a few Laplace transforms, and then we'll do a few inverse transforms, and then we'll solve a differential equation. Okay, let's take a look at this one right here. Move that up like that. Okay, I just have a u sub 3 there. Okay, so that tells me I'm going to be using the second shifting theorem when I have a u sub a. What is the function that's right next to it that's being multiplied by it? Well, in this case, it is just 1. And I identify that as g of t minus a, or in this case, g of t minus 3. So g of t minus 3, and I'm getting that from this a here. This equals the other part that's not circled in blue, so this equals 1. So I jump to the first stone. Now I have to figure out what g of t is. Well, you could say replace all the t's in that equation with a t plus 3, and you'll end up getting that. And really, this is just a horizontal line if you're thinking about it, and we just shift it 3 to the right or 3 to the left, and you end up still getting the same line if you want to think geometrically. Okay, so now I'm in the middle of the river, which took me a while to get there on the last problem, because I had to do Pascal's triangle or multiply out a binomial a few times. And now I'm going to jump to g of s, capital G of s. And hopefully you've remembered what the Laplace transform of a constant is. Remember that constant's t to the 0, so that's 0 factorial over t to the 1, or s to the 1, and so you end up getting 1 over s. I kind of messed up saying that. Okay, so now I'm on this stone right here, and I'm following this road map here. So my last one is going to be write the whole thing there, jump to the shore. I'm going to go e to the negative 3s all over s. So that's what I'm going to write. So this is e to the negative 3s all over s. So I multiplied this last one by e to the negative as. There's the answer, and that gives me the Laplace transform of u sub 3. Now you might guess that the Laplace transform of u sub 5 would be e to the negative 5s over s. So the more you work with these, the more you start memorizing some of these basic ones, you know, because this could be part of the driving function of a differential equation. Let's go ahead and do our last Laplace transform before we hit the inverse transforms. And that will be problem number 4. And problem number 4 looks like that. So there's my river, and there's this. Now if I had planned correctly to have the river and all that stuff be in each thing, I would have put it on the left side. But oh well, I'm not going to stop the video and redo this all again. Wouldn't get any videos done if I always did that. Okay, so I don't think I cut off any of the function there. I think you can see everything. Maybe you don't need the river anymore. Maybe you don't need that drawing, but I sure do, because it's the only colorful part of this lecture. I mean, look at. Let's go ahead and identify the fact that this is u2, which means I'm doing a second shifting theorem. And that means I'm going to identify the rest of the function as g of t minus a, which is g of t minus 2. So let's write that down. So I have g of t minus 2 Now at this part, some of you, when you do a lot of these, you might say, oh, let's just say g of t minus 2 and point it to this part and circle it or whatever. I'm going to write it all out here. This is e to the negative 3 t minus 2, and then we have the cosine of 5 t minus 2. So we are on the first stepping stone, and now we want to jump over here to g of t. Now, this is not going to be so bad because all the places you see t, well, you actually see t minus 2. So I can replace each of those t minus 2's with just a t. So g of t is e to the negative 3t cosine of 5t. Okay, now here's the tricky part here. We are supposed to take the Laplace transform of this, and I have an e to the negative 3t. And so sometimes, and I will only say this joke one time, sometimes when you are doing shifting number 2, sometimes when you're doing number 2, a little number 1 comes out. And that's what's happening here. We're going to do shifting theorem number 1. And I mean, I'm not going to say this is g of t, but I'll just say that this is the other function. I'm going to ignore that red part and do the Laplace transform of the cosine 5t. The Laplace transform of the cosine 5t is s all over s squared plus 25. So that is what the Laplace transform of cosine 5t is. And then I'm going to account for the first shift by going a minus a. In this case, a is different from the a that we have here. So this is going to be plus 3 here and plus 3 here. So this is a first shifting theorem done within the second shifting theorem. And that's how it usually goes. First shifting theorem is done inside the second shifting theorem. And I am now standing on this rock right here. I'm ready to jump to the shore. The only thing I need to do to jump to the shore is multiply this guy by e to the negative 2s. See, that's what we have. We found that guy right there. So let's go ahead and officially write out our answer. F of s equals, we'll say e to the negative 2s. Okay, let me just, okay, e to the negative 2s. And then we have, then I'll multiply it by this. So this is s plus 3 on the top. And then on the bottom we have s plus 3 squared plus 25. I'm not going to put the plus 3's in red now. And this is the Laplace transform of that function there. And sometimes when you're solving differential equations, this does happen. You might think, oh, well, Joe, you just set this up for us so we can do the problem. But sometimes your driving function, everywhere there's a time, it says t minus 2 or t minus 5. So that completes problem number 4 of finding the Laplace transform. Now we're going to go ahead and find a few inverse transforms. Okay, so we're going to start off on this bank of the river, and then we're going to jump across and get over there. So that's what's going to happen. So problem number 1. Find f of t, find the inverse transform. And so there's the river. There's my Laplace transforms. I guess I could put this up here this time. Okay, so that's cool. I'll keep bumping into that. And let's see if we can do this problem. I am now in the land of s, and I have an e to the negative 3s. So when you have an e to something in the land of s, what I'm going to do is I'm going to circle it in blue, just to identify that I'm doing the second shifting theorem. I'm right here on the shore, and now I'm going to identify what g of s is. G of s is the part that's not the blue. So let's go ahead and write that down. G of s is 1 over s plus 2. Okay, I'm standing on this rock now. Now I want to jump over to the inverse transform of g. So this is g of t. G of t is, hopefully you've remembered some of your transforms. This is going to be e to the negative 2t. Okay, so we just jumped over to there. Now we're in the middle of the river. Now the rest of this going back when you're doing inverse transforms on the second shifting theorem is not so bad, because now all I'm going to do is go g of t minus a, and in my case, what is a? A happens to be 3, and remember a is always going to be positive, so it's g of t minus a, so this is g of t minus 3 equals e to the negative 2 t minus 3. Okay, so I'm standing on that rock and I'm going to jump to the shore by multiplying this thing right here by u sub a, u sub 3. So f of t equals u sub 3 of t times e to the negative 2 t minus 3. We don't have to distribute that. You could if you want. And there's your final answer. And all these problems we do where we're finding the inverse transform, you could cover up all your work and go ahead and cross the river the other way. You'll end up right there for your final answer. Okay, let's go ahead and do 3 more of these. I know that sounds like a lot, but these 3 more problems are going to cover a lot of things. So I might as well just, I don't usually do this, but I'm going to do this time. Here's 2. Here's 3. Here's 4. Okay, so that's weird that I would show them to you. Those problems, I'm finding the inverse transform on, and they almost look the same. The only thing that's different in those problems is this little number here. This is a +1 here, and a -3, and a +2. That shouldn't make a big difference. Oh, it's going to, and there's going to be 3 different things that happen, 3 different methods when you're doing these problems. So I wanted to actually show them all on the same screen so you kind of know what I'm going to do next. So this one right here, you have f of s equals that. Okay, so let's move this down. We'll go like that. Okay, so there it is. What am I going to do with this? And hopefully this is coming out all right. I don't want it to be blurry because some of the paper's popping up. Okay, I see the e to the negative 2s, so I know I'm doing a second shifting theorem. Okay, so the next question is, can I factor the bottom? And the answer to this question is, yes, I can. Okay, but before I get to that, I think I should jump over from here to this stone. So the first stone is g of s, which is everything that is not the blue part. So this is 1 over s squared plus 2s plus 1. So the question is, can I factor that? And the answer is yes, and I'll write this out again. So this is g of s equals 1 over s plus 1 quantity squared. So it factors as a perfect square trinomial. It factors into that. And now I'm standing on this stone and I'm ready to jump using the inverse transform. But to do that, I notice there is a +1 there. There is a shift. So this is another example of when I'm doing the second shifting theorem. Now I'm going back, and as I'm doing the second shifting theorem, a little first shifting theorem comes out in this problem. So look what we have here. Circle that in red. I'm going to ignore the +1 temporarily, and I'm going to write g of t. G of t. So I ask myself, what is the Laplace transform of 1 over s squared? Or it's actually set up nicely. It says 1 factorial over s squared. That Laplace transform is t. Okay, now I've got to account for the shift in the first shifting theorem. I'm going to multiply this by e to the negative t power. So that is what g of t is. I'm standing there and I'm ready to make the jump to the next stone. So here's the jump to the next stone. G of, let's see, my a here was 2, so this is going to be g of t minus 2 gives me t minus 2 e to the negative t minus 2 power. Okay, so I'm standing right there and I'm ready to jump to the shore, and as I'm looking at this, all I have to do is multiply this guy right here by u sub 2. And so that's what I'm going to do, and I'm going to get my final answer, which will be little f of t is u sub 2 of t times that. And then we'll talk about what people do when they cross rivers and they get really good at jumping from stones to stones. Well, maybe you can think about what I'm going to do. What happens when people start getting really confident and they're crossing rivers? Well, the thing that people do is sometimes they're like standing here and they go like, well, I'm really good at this and I'm going to jump to the shore. Is that all right? Yeah, I mean, it all depends on your skills. So some people are going to go like right here and they know that they can combine this step and just jump right here. So if you're super lazy like I am, sometimes you'll jump there. Because I'm teaching this, I will always write out all the steps. Okay? Especially we're doing a video and we have no room for someone to say, wait, instructor, stop. Well, can you explain what you did here? So that's the disadvantage of these videos. The advantage is you can stop it, have lunch, and then come back, or stop it, try to work the problem yourself, and then continue it. The disadvantage is there's not the interaction. Okay, let's go ahead and now do the next problem, number 3, where instead of a +1 there was a -3. So how's that going to work? Let's see. Okay, so what do I have here? I've got the river, and I've got, let me just put this centered right here, and then I've got the shifting theorems. Okay, so I say, wow, look at this. This is second shifting theorem. I'm finding the inverse transform, and so I am jumping to the first stone, g of s. G of s is 1 over s squared plus 2s minus 3. So the question is, can I factor the bottom? Last time I was able to factor it into a perfect square. This time, let's see, factors of 3 that subtracting give me 2, that would be 3 and 1. Plus 3 minus 1, so it looks like we can factor this into 1 over, and what do we have? S plus 3, S minus 1. Remember when you used to take math classes and you used to raise your hand, and I did this too, okay, and used to say, oh, teacher, I have a question after they just factored a trinomial. Can you put the S minus 1 first? And then the teacher would go, yeah, and you know, maybe she was teaching for 30 years. She's like, how many times do I have to tell you? And then it would be funny because then she'd do another one, and I remember like having asked that, and then the next one, she wrote out the answer, and it was a different problem, different trinomial. And then someone like in the front raised their hand, and they're like, could we put those in the other order? And then I was like, man, that would suck to be a math teacher. Ooh, the irony. Now I am the math teacher. So the video makes it so I don't have people ask those questions, and I just brought it up, but you can put those in any order. Now I'm going to go ahead, and I'm standing on this rock, and I'm ready to jump. But it seems as if I can't make the jump because I have to do something that you probably don't want to see. It's gonna start with a P, partial fraction decomposition. So here it goes. Let's move the river and everything out of the way because we have to concentrate on this. This is not going to be the worst partial fraction decomposition in the world, but let's go ahead and put this up. 1 over s plus 3, s minus 1. So I'm just sort of taking this problem off to the side, or you know, below, and doing this. This is a over s plus 3 plus b over s minus 1. I'm going to multiply by the LCD, so I get 1 equals a times s minus 1 plus b times s plus 3. I'm going to go ahead and put values in like s equals 1 and see what happens. I have 1 equals. The first guy is dead, 0, and then the second person here is b times 4. Oh, I hate when these guys are fractions, but oh well. It is what it is. What are you going to do about it? Okay, and then I'm going to go s equals, in the same equation right here, s equals negative 3 to 0 out the other guy, and I'm going to get 1 equals a times negative 4 plus 0. So this a equals negative 1/4. And so it looks like my partial fraction decomposition, which is right here, is negative 1/4 over s plus 3 plus 1/4 over s minus 1. Okay, so that was my partial fraction decomposition. I'm going to need another piece of paper now. And what are we doing? Okay, so that was my g. Okay, so my g of s. Okay, so, and I'll go ahead and put the river back up after I write this down. So g of s, I think we got our foot wet on this one. You know, we're standing on that rock and we're trying to reposition. Look at this. And we're ready to make our next jump. But we really had to reposition here. And so that is what g of s looks like. Okay, so there it is. Maybe I'll try to go like that. I don't know how much of this I'm going to fit. Okay. So here's the river. Here's the Laplace transforms. I like to have layers of papers here just to do this problem. I can cover that one up a little because I already know what it is. And let's move this down a little. Okay, we'll just do that. Okay, so I'm right here, and I've been like, oh, it's been a while since I've been able to jump to another rock, and now I'm going to. And so g of t is equal to negative 1/4 is just a constant, and then the inverse transform of 1 over s plus 3 is e to the negative 3t. Then I have this guy right here plus 1/4, and then the inverse transform of 1 over s minus 1 is e to the t. And so now I'm on the middle stone, and some of you are going to jump to the shore from now, but I'm just going to go ahead and take this baby steps here. G of t minus a, so it's going to be t minus 2, happens to be negative 1/4 e to the negative 3 t minus 2 plus 1/4 e to the t minus 2 power. So let's go ahead and write out the last step. We're here. I'm going to jump to the shore. This is f of t. My original f is up there. And looking at the second shifting theorem, I'm going backwards, and I should multiply this part that I found by u sub a, or u sub 2. So u sub 2 of t times that. So I'll go ahead and put some parentheses, or maybe brackets. I don't know. You can pick. Negative 1/4. Some of you would have factored the 1/4 out or something like that. And we have e to the negative 3t minus 2 plus 1/4 e to the t minus 2. And there is the answer. So look, we've seen two problems where the bottom factors nicely into a perfect square. And that was, we used the first shifting on that in this step. And then we saw where it factors over the rational numbers. And we used partial fraction decomposition. A lot of that is covered up because, you know, that creates fear. And you have to think, well, what will happen? What else could happen with a quadratic on the bottom? Well, maybe the quadratic does not factor over the rationals. And some of you are like, oh, let's do the quadratic formula. But let's hold off on that. I'm going to change that negative 3 there in this problem to a positive 2, and that's going to become problem number 4. So let's get rid of all this junk here. And you might already know how to do this one. I think we've done a problem. Well, we haven't done the second shifting theorem, but something's going to seem familiar in this problem. So let's go ahead and identify the fact that we are doing an inverse transform and there's an e to the negative 2s, which means I am doing the second shifting theorem. So my g of s, that's the part that I am identifying there. G of s is 1 over s squared plus 2s plus 2. And then I say, oh, factors of 2 that add up to 2, it's not going to happen. So this does not factor. So what are we to do on this? I mean, we are stuck on this stone. We want to jump there, and how can we do this? Some of you may have remembered when we did a problem like this. Watch this. S squared plus 2s, leave a space, and put a plus 2. So maybe now you know what we're doing. You know we are completing the square. I'm going to take that 2, chop it in half, and square it. So 1 squared is 1. So I'm going to add 1 there and subtract 1 there. Okay, so what does this give me? This gives me 1 on the top. And on the bottom, I have, this is s plus 1 squared, s plus 1 squared, and then plus 1. Now, can I take the inverse transform of that? Almost, it reminds me of like a sine, except there's an s plus 1 there. Well, look at this. This is another instance of doing shifting 2, and in the middle of shifting 2, you have a little 1 there. So we got to take care of that. I'm going to circle that plus 1 and ignore it temporarily. Now I'm jumping to the next stone. This is g of t equals the inverse transform of 1 over s squared plus 1. Well, you have a b squared is 1 and b is 1, so it looks like it's going to be the sine of t. And then let's account for the shift. The shift is e to the, and you could look up there to see what's going to happen. It's e to the negative t. And so now I'm in the very middle of the river. I'm now going to jump here and write out what g of t minus 2 is. This is e to the negative. Then we have t minus 2. Sine of t minus 2. And then I'm right here and I'm ready to jump to the shore. And if you're just looking at the second shifting theorem, I've just computed g of t minus a. I'm just going to multiply that by u sub 2. So just multiply that by u sub 2 and you'll be done. So f of t equals, where's my blue pen? U sub 2 of t. And then we have e to the negative t minus 2. And then sine of t minus 2. And there's your answer. And it might be the case that you go do your answer and then you look in the back of the book and it's completely different because they decided, hey, let's do the trig sine addition identity for some stupid reason. But isn't that always the case? You know, you get your confidence up, you look at the back of the book, you tear up your homework and then realize, oh, they just did something crazy. Let's go ahead and do our last problem from this section. We'll take that off. And that would happen to be this differential equation. Solve y double prime plus y equals f of t, where f of t is in this picture, and we have y of 0 equals 2, y prime of 0 equals 1. This is the power of Laplace transforms. So sometimes your driving function may be piecewise defined. Sometimes in terms of circuits, it might go on and then shut off, and then go on and shut off and go on, and it might be periodic. We did skip the section about periodic functions, but it could be lots of different things, and this is the power of Laplace. So in order to do this, I'm going to have to figure out what this function is in terms of the unit step function. So that's what I'm going to do right now. you could, if you want, and I'm not saying you have to do this, this f of t, you can write out the piecewise defined functions. Some may be able to go from this picture right to what we want. So f of t is, well, this looks like it has slope 1. It looks like it's just going to be t. And then the rest of the way it's going to be y equals 1. And so this is if this is t is between 0 and 1, so 0 less than or equal to t less than 1, and then this is t greater than or equal to 1. Okay, so how are we going to write this as a unit step function representation? Well, we did this in the last section. We're going to say, okay, the function is t, and then after that, okay, so there were two methods that I showed you. One method was saying u0 minus u1, and then we took the next one, which was 1, so that's what the function is, and then we turn that thing on at, turn that function, light it up at 1, and then just keep it going for the rest of the time. So that is how we did it. Let's go ahead and rewrite this. This is going to be f of t equals, this u1 is just a 1, so we'll have t minus t times u1 plus u1. One more step. F of t equals, we're going to write this as t, and then I'll factor out a u1 of t, and this is going to be minus t plus 1. So we went ahead, so there was a reason we did the last section, because we knew this was going to happen with differential equations. So what I'm going to do next is I'm going to go up to this differential equation and rewrite it. So this says y double prime plus y equals this guy right here, which is t plus u sub 1 of t, and then we have this right here, negative t plus 1, which some of you could write like 1 minus t if you'd like. Okay, so a lot of your problems in the homework will be given to you like this. And then near the end, they'll just start giving you some pictures for the driving function. And this right here is the driving function of the differential equation. So what I'm going to do on both sides of this equation is I'm going to Laplace both sides of this equation. And I've got to remember like what the Laplace transform of y double prime is. Well, that's the one where it's s squared L of y. Then we have plus s y of 0, and it's not a plus. So yeah, so here I am saying you have to remember this, and it's actually going to be minus for the rest of them. So this is minus, and then this is minus y prime of 0. Okay, so that's that first part. So that's this part right here. Orange, and there's orange there. And then we have plus the Laplace transform of y. So on this one we don't get to do sly minus yo because we don't have just a single y prime there on the left hand side. Okay, and then what are we going to do? Then we're going to do the Laplace transform of t, and this was bad planning here, wasn't it? This is going to be plus the Laplace transform of u sub 1 of t, then we have negative t plus 1. Okay, so I'm ashamed. Look at this. It's just running into everything. So how am I going to do this? Let's see if we can do this problem. First thing I want to do is I want to realize that the L of y's, I'm going to set them equal to w, so I have s squared w. Y of 0, so what is y of 0? Y of 0 is that guy right there. It's 2, so this is going to be a 2 right there. And y prime of 0 is 1. So there's a 1 right there. Hopefully that color shows up on the PDF. So we have minus 2s, and then I have minus, wait, I forgot something. Minus 2s. Did I forget something? I don't think I did. Okay, sorry. Minus 1, and then I have a plus w. That's this guy right here. He's w. Okay, so this equals the Laplace transform of t. The Laplace transform of t is 1 factorial over s squared, so this is 1 over s squared. Okay, so this right here, when I'm taking the Laplace transform of u1 times that function, I'm doing the second shifting theorem. So let's see if we can be a little bit more efficient here. I'm going to circle this in blue. And I know that when I do the second shifting theorem, that I'm going to have this right here. I'm going to have plus. So see what happens here. We have u sub a. We know that this is going to be e to the negative s, because there's a 1 there, negative 1s. So this is going to be e to the negative s. And that's going to be multiplied by something. Okay? So I'm actually doing the stepping stones, and I'll do them down here. So let's just go ahead and do them down here. I identify the g of t minus 1. Okay. G of t minus 1 is the stuff that is not the blue part. So it would be negative t plus 1. Negative t plus 1. I go ahead and replace all the t's with t plus 1s. So I have g of t equals. So every t gets replaced with a t plus 1. So g of t equals negative t minus 1 plus 1. And so this would be negative t. So that's what g of t is. And so look, g of t is sort of the middle of the river there, and then I'm going to find out what g of s is. G of s happens to be negative 1 over s squared. And then I'm going to multiply that by e to the negative 1s, which I have right there, so I'm pretty much done with this. This is negative 1 over s squared. And yes, I left a lot of room, didn't I? And so that is what we did. This was the second shifting theorem. And that's how we got that right there. So let me say we popped out of the cloud and got that right there. Okay. Now on the left-hand side, I have two occurrences of w, so let's just put those guys together. S squared w plus w. And what I'm going to do is I'm going to go ahead and bring the 2s and the 1, the negative 2s and the negative 1, to the right-hand side of the equation. So I'll have 2s plus 1, and then I have plus 1 over s squared. And then this is going to be minus e to the negative s over s squared. So that's what I have now. And then we're always asking, should we put some things together? You know, the 2s plus 1, should we put it together with the 1 over s squared and get a common denominator? You could if you want. The thing that you do not want to mix ever when you do these problems are the things that have the e to the negative as, or e to the negative s in this case. You don't want to mix those with the other ones and get a common denominator, because you will burn yourself. Try it out and see what happens, but you'll be crying at the end. Let's go ahead and factor out a w, and I have an s squared plus 1. This equals the right-hand side, so I guess I just will write it again. Okay, I think I'm going to need another piece of paper. I thought I could fit it all on one paper. No, I didn't think I could fit it on one paper. So, wow. I'm not going to put the 2s and the 1 with the 1 over s with one fraction, because when I divide by s squared plus 1, I can find the inverse transform of 2s over s squared plus 1. That's going to be like some sort of cosine thing. So let's go ahead and keep all 4 of those terms separate. And I have w equals, what does w equal? 2s all over s squared plus 1. And then the next one's going to be plus 1 over s squared plus 1. And then this one's going to be plus 1 over s squared plus 1. And then this is going to be minus e to the negative s. Now look what I'm going to do. I'm going to go ahead and put it like this, and then maybe you could wonder why I did that. S squared plus 1. Well, the reason I did that is because I am going to have to do a partial fraction decomposition right there. But when I do it for that term, this is exactly the same thing. So I'm getting like a 2 for 1. I'm going to do partial fraction decomposition. It will count for both of those. So let's go ahead and draw a line and focus our attention on partial fraction decomposition. Our favorite thing to do, I guess. I don't know. Let's do this. So this is 1 over s squared, and then we have s squared plus 1. So I'm going to treat this as a linear factor and build it up. So I'm going to go like this. I'm going to go a over s plus b over s squared. Now, when it's just an s, you can do it this way, or you could have gone as plus b over s squared, which is exactly this right here. As plus b over s squared is this. So I decided to treat that as a linear and build it up until I got a 2 there. And then I do have a quadratic factor, and this is going to be cs plus d all over s squared plus 1. I'm going to multiply this equation by the LCD. The LCD in this case is s squared plus 1. Let's go ahead and do that. This is kind of a long problem. We end up getting 1 on the left-hand side, because all those things cancel, and then one of the s's is going to cancel on this term here, so I'll have s squared plus 1, and then over here the s squareds are going to cancel, and we'll have b s squared plus 1, and then over here the s squared plus 1s are going to cancel, and I'm going to get plus cs plus d s squared. Okay, now I have to solve for a, b, c, and d, and I'll chisel away at this. I'm not going to get much done by chipping away, but I always chip away when I can. S equals 0 is the only thing that's going to give me a result. So I'm going to have 1 equals, that guy is dead. This guy says, what does this guy say? It says b times 1. And then this guy over here, because of that s squared, he's dead as well. So this gives me b equals 1. So b is 1, and there's nothing else I can do to chisel it away. Some of you are like saying, why don't you let s equal the imaginary number I? I'm not going to do that. I'm going to go ahead and take this equation right here and distribute and equate coefficients. You know, that's what I'm going to do. So I have 1 equals as cubed plus as plus s squared plus 1 plus cs cubed plus ds squared. Okay, now what I'm going to do is I'm going to look at my s cubed terms. And the s cubed term on the left-hand side is a 0 s cubed. So I have a plus c equals 0. And that comes from the yellow part here. Okay, now I'm going to look at my s squared terms. And the s squared on the left-hand side is 0 s squared. So look what I have here. I have 1 plus d equals 0. And that came from those guys there. And then I'm going to look at my s terms, which I will underline in orange. The s term on the left-hand side is 0s. So it looks like a equals 0. And you might ask yourself this question, can that happen? And the answer to that question is, it just happened. And then the last one, and this is rather silly to do, but I'll do it anyway. I'll underline all my coefficients. And actually, it's a good thing that we have 1 equals 1. If we had 1 equals 5, you know, we'd run out of the room. I'd turn off the video and cry. So there it is. So A is 0. What does that tell you about another letter here? C. Look at this. If you put this over here, this tells you that C is 0. This one here tells you that D is -1. So let's circle those, and that one's already circled. So our partial fraction decomposition, you know, this part right here can be rewritten. So it says A is 0, so A over S, so that's gone, and you'll have B over S squared, so this is 1 over S squared plus C is 0 and D is -1, so it actually probably should say 1, well, I'll just write it like this, -1 on the top and an S squared plus 1 on the bottom. Wow. Okay, so that is the result that we got for doing partial fraction decomposition. So we have that right there. And so I'm going to, I'm trying to think of colors I haven't used. I've used orange. I don't want to use red, and I'm just going to have to repeat something, I guess. Wait, I have not used green. Okay, well, I've used that green, but not dark green. So I'm going to go ahead and say, look at this. I've just found the decomposition of this. So this right here gets replaced with that. And so does this right here. Okay, so I'm going to need another piece of paper. That was a crazy differential equation we're doing. Let's copy this down. I'm going to replace the w with what it really is, which is L of y. And so this equals 2s all over s squared plus 1 plus 1 over s squared plus 1. And then we have our partial fraction decomposition yielded this. It gave us plus 1 over s squared minus 1 over s squared plus 1. That's that green part right there. Then we have minus e to the negative s. And then over here we have 1 over s squared minus 1 over s squared plus 1. Wow, that's crazy. Okay, so now what we're going to look at is we're going to say we see something before we inverse transform it. We have like terms right here. We have 1 of these creatures and -1 of these creatures. So when we thought we would see the sign come out of those, well, those guys are gone. And so now I have that right there. And let's see, I have 1 actually over s squared. Okay. So I have 1 over f. Okay. Let's continue here. I think I'm doing this right. I got the feeling like maybe I was doing something wrong, but oh well, we'll just go with it. Let's see what happens if we roll with the punches here. gonna take the inverse transform of the inverse Laplace transform of the Laplace transform of y. That's a tongue twister. This is y. The inverse transform of 2s over s squared plus 1, that is 2 times the cosine of t. Those guys canceled out. The inverse transform of 1 factorial over s squared is just going to be a t. Okay, and then we have this fun part right here. So let's go ahead and bring up the second shifting theorem. The second shifting theorem, I'm taking the inverse transform of this, and look what I have. That tells me the second shifting theorem. I'm going back, so that's going to become really a u sub 1. So this is minus u sub 1 minus u sub 1 of t. And then what I'm going to do in here is I'm going to go ahead and identify this part right here. So I'm kind of crossing the river again without actually putting the river drawing there. And this guy right here is g of s. G of s is 1 over s squared minus 1 over s squared plus 1. And then the next stone would be going g of t, because we're trying to get at g of t minus a, or g of t minus 1. So this is g of t. I'm taking the inverse transform of 1 over s squared, which I believe, we did over there, and this is going to be t. And then the inverse transform of this guy, which is minus sine t. And then I'm going to go ahead and I'm going to write g of t minus 1, which is t minus 1 minus sine t minus 1. And so I'll put this in a cloud, just like I did the other one. This is me coming across the river, and I was doing the inverse transform there, and I ended up getting t minus 1 minus sine, and then this is t minus 1, and there it is. Wow. So that finishes the problem. And so we've jumped out of that cloud, and that helped us get across the river. So this was the second shifting theorem. And there's the answer. So, and some of you are like, what did we do? I don't even know. What did we do? Oh, we solved this differential equation, which had these initial conditions, and the graph looked like that. So in your homework, you'll be, the first part says find the Laplace transform, and you'll do some of those. Find the inverse transform, you'll do some of those. That's the second shifting theorem. And then they'll say solve these differential equations. So that completes 10.7. You're done. I might put a little extra bonus material at the end of this lecture. Some of you might want to just turn off the video now. Okay, so this is 10.8, which is the Dirac delta function. You are not going to have to do any homework over this. This is just for the extra motivated student. Some of you are going to be taking linear analysis 2 at Cal Poly, so maybe you might see some of this. Let's take a look at what we have, what this is all about. So sometimes this has another name, the unit impulse function. And so we've seen the unit step function, which looks like that. It's 0 and then it becomes 1, and that helps us with a lot of problems. The unit impulse function is what happens like when a large magnitude acts for a very short amount of time. And so this could be, maybe you're an engineer designing the wing of an airplane, and you have to anticipate lightning, or you're designing something with golf clubs hitting a ball. And so the unit impulse, or the Dirac delta function, kind of looks like this. So there's nothing happening here, and then like right away, a very short amount of time, it spikes. The magnitude spikes, and then it goes back to nothing again. So that happens in the real world, and we like to solve differential equations where the driving function is the unit impulse function. So this is going to get a little weird, but let's see how we do with this. We're going to define delta sub w equal 1 over w, 2w between negative w, and then 0 otherwise. So what does that graph look like? It looks like that. Now, if you go to look at the area under the curve of that graph, the area is actually 1. From negative infinity to infinity, the area is 1. So let's go ahead and define this Dirac delta function, or the unit impulse function. It is going to be delta of t equals the limit as w goes to 0. So we're taking this interval here and shrinking it. And as it shrinks, what happens to this? This gets smaller, but it pops up higher and higher and higher and higher. And so that's what's going to happen. That is what the unit impulse function is. So it pops up to infinity. So we've got to watch what we say. So I put those in quotes. It's not a function at all, because when w goes towards 0, you almost get something like a vertical line test, vertical line which does not pass the vertical line test. And the integral from negative infinity to infinity of delta of t still equals 1. So it's kind of a crazy, crazy function. And good thing you don't have to do this in your homework or on the exams. And so we can put this function wherever we like. So we can go delta t minus a, so we're shifting it. And so it's 0 when t does not equal a, and infinity in parentheses, quotes, when t equals a. What does the function look like? How would we draw that? Something like that. So here's the deal. When you go to do the definition of the Laplace transform on the Dirac delta function, or the unit impulse function, those are the same things, you end up doing it, and you end up getting the Laplace transform of that thing is e to the negative sa. So it actually becomes very doable in terms of the math. That's 10.8. Let's go ahead and look at what's in 10.9. 10.9 is called the convolution integral. And let's just take a look at an example. So you'll know what a convolution is, and once again, you're not going to be tested on this, or you don't have assignments on this. You've got an example of f of s and g of s, and those are some rational functions. And if you look at their Laplace transforms, the Laplace transform of 1 over s squared is t, and sorry, the inverse Laplace transform, and the inverse transform of that one is e to the 3t. So I'm going to do this. I'm going to say, what is the inverse transform of f times g? So we'll write it out. So that's what it is. And then you're like, oh no, I've got to do partial fraction decomposition, and I'm not going to go through all those steps. But now you can take the inverse transform of each of these. This one's negative 1/9, and this one's going to be negative 1/3 t, and then this one's going to be 1/9 times e to the 3t. So that is what I want to write down there. And so I have that. That's the answer. But the painful part was doing the partial fraction decomposition. Okay, so here's something that you can do, and it's helpful on some problems. But before we get to that, we want to realize that the inverse transform of fg does not equal the inverse transform of f times the inverse transform of g. Okay, so that is not the case. So you might say, well, I thought it was a linear transformation. Linear transformation you would have a f plus g there, not f times g. So those vectors cannot be multiplied. So that can't happen, and let's just verify that. The inverse transform of f, we already have it up in the top right corner, you know, is little f and then little g, which is t e to the 3t. So we know t e to the 3t is not the same as what we got. So this, you cannot just multiply the inverse transforms when you have a product here. Okay, let's take a look at another way of doing this, and this is probably going to blow your mind here because it's going to be new ideas. There's another way of doing this, and well, let's just go ahead and show you what this is. This right here, when you go F with the star and a G, that's called a convolution. Okay, it's a new word. And the convolution theorem says that if you take the inverse transform of a product, that it is the convolution of their inverse transforms. Okay, so I have not showed you what a convolution is. So the convolution, this is a definition of the convolution integral. It's from 0 to t f of t minus w gw dw. Wow. So you're trading the pain of partial fraction decompositions for the pain of doing this kind of convolution integral. So let's go ahead and plug t minus w into f, which would just give you f of t minus w would be t minus w, and then g of w would be e to the 3w. So let's plug that in there, and that's what gives us the integral. We're integrating with respect to w. T is a constant. So I would actually have to do, and I'm not going to show you the details of this, I would do integration by parts. And I get that from 0 to t. I would evaluate this at t and 0 using the fundamental theorem of calculus, and I would end up getting that. And distribute the negative, you end up getting the same thing. So 10.9 goes over something called the convolution integral. These are just some topics. We can do Laplace transforms of integrals. We can do lots more with Laplace transforms. This class was just an introduction to Laplace transforms. This ends this chapter, and you guys have a good day.